This is going to be our first video from Chapter 15, looking at acids, bases, and salts, covering sections 15.1, 2, and 3. The goal of this chapter is to help you identify the structure and formulas for both acids and bases and what they're going to do in chemical reactions. The basis of acids has to deal with hydrogens, and so we want to quickly review the concept we talked about in the last chapter, understanding a hydrogen bond. And so we can see here on the left hand side we have our nitrogen that's attached to a hydrogen, and so we know that those types of molecules can hydrogen bond, while the molecule on the right doesn't have a hydrogen connected to a fluorine, oxygen, or nitrogen, so cannot hydrogen bond. There are different ways different scientists like to describe acids, and what I want you to know here is the definitions for the Arrhenius acid, Arrhenius base, a Bronsted-Lowry acid, and a Bronsted-Lowry base, and then also a Lewis acid and a Lewis base. Our Arrhenius and Bronsted-Lowry definitions are dealing with hydrogens, whether they're going to accept them or donate them. Our Lewis difference is that we're looking at electrons, so a Lewis acid would be an electron pair acceptor, and a Lewis base would be an electron pair donor. So let's look at these with a chemical reaction. We can see here we have hydrochloric acid plus water, giving us our hydronium ion and our chloride ion. So we can see here that HCl is acting as our acid because it's donating, it's giving up its proton, while our water is acting as a base and it's accepting its proton, meaning we have 3 hydrogens instead of only 2. We actually also can compare these looking at conjugate acids and base pairs. This concept's a little bit too advanced for us, but if you end up continuing with the chemistry, this will become really important. And so our base and conjugate acid are a pair, and our acid and conjugate base are also pairs. Basically, they're 2 species that differ from each other by the presence of just a hydrogen ion. So for our Lewis acids, we can see here on the left we have our boron trifluoride and our ammonia, and we have this extra electron pair that's on our ammonia, so it's going to donate that to our boron trifluoride and give us our new molecule. And we can see here that our acid in this case is acting as accepting that extra electron pair. So familiarize yourself with these 6 definitions. In general, let's look at some reactions of acids. We can combine them with metals, giving us a salt and a gas. We can combine them with other bases, giving us another salt and water. We can combine them with our metal oxide, so a metal with oxygen attached to it. And we also can combine them with any carbonates, giving us sometimes our water and a gas as a byproduct as well. So in general, we can see here we have hydrochloric acid, an acid we've talked a little bit about in the course, giving us our salts, magnesium, calcium, and sodium chloride. Our bases actually can be something called amphoteric, which means they have the ability to act as an acid or a base, depending on whether or not they're accepting or donating a hydrogen. These are some more quick reactions looking at as a base. What it ends up doing is it ends up giving its hydrogen away, creating water. And then also as an acid, we can see that it ends up taking away an OH group and expanding on how many they have. So we have a sodium zinc hydroxide solution. We also can see them acting or reacting with metals, similar to what we see with bases, and here we're generating a much larger compound where we have sodium, aluminum, and hydroxide all together. But in general, what I want you to know is if we look at base, we look at metal, and we look at water, we're going to see a creation of a salt giving hydrogen. And again, some of the compounds we've talked about, most of them, or the bases that are most common, are going to be our hydroxide groups. And in this case, we're going to look at making sure we see ionic compounds that are going to have cations and anions from the acid. So remember our polyatomics and remember what type of ion the element's going to act as depending on the location of the periodic table. When we have compounds that end up separating, we often have them being called electrolytes. So we've heard this in Gatorade beverages, anything that you have after a post-workout, you want to have high in electrolytes, and that's because we're losing electrolytes when we're sweating. And so what I want you to have an association here is that when we talk about elements that have a charge or ions that have charges, so on our left-hand side in the electrolytes column, we have our sulfuric acid, our hydrochloric acid, other acids, things that we've talked about having a positive and a negative charge, and on our non-electrolytes, things that are not going to separate, things that aren't associated as ones having our ions. We do see some OHs in here, but in general, we do not see two separate groups having a positive and a negative charge, and that's how you can tell whether things are going to be electrolytes or not. So our dissociation, we actually see ions becoming charged and surrounding themselves with the side of the water molecule that they are most attracted to. So we have our sodium plus cation attracting to our partially negative side of the water, and we see our larger negative anion chlorine being attracted to our hydrogen side of the water. And so just keep this in mind as why we see these salts dissociate and how we can focus on which ions they're going to be end up and what charges they're going to have. So when we look at our examples here, which compound will not dissociate in water, we can say that HCl we've talked about as having positive and negative charges. Same thing with potassium bromide. Same thing with sodium hydroxide. Our CH3OH group are going to be what's known as organic. It's not going to be able to dissociate, so it's a non-electrolyte. And so we can look at these based on molecules we've practiced with naming, and also ones that we know we can say that this is how those individual elements in a compound are going to act. If we see an anion and a cation, we know they're going to dissociate.